How cruise missiles work. Introduction. Cruise missiles represent one of the most sophisticated weapons systems in modern military arsenals, combining advanced propulsion, navigation, and guidance technologies into a single autonomous platform. Unlike ballistic missiles that follow high-arching trajectories through space, cruise missiles are self-propelled, unmanned vehicles designed to fly at relatively low altitudes, while navigating complex terrain to reach their targets with remarkable precision. These weapons emerged during the Cold War era as a response to the need for accurate OTH, long-range strike capabilities that could penetrate enemy air defenses by flying below radar detection thresholds. Today's cruise missiles incorporate cutting-edge technologies including GPS navigation, terrain-following radar, digital scene-matching systems, and artificial intelligence algorithms that enable them to autonomously adjust their flight paths in real time. Their ability to deliver conventional or nuclear warheads across hundreds or thousands of miles with pinpoint accuracy has fundamentally transformed modern warfare tactics and strategic military planning. As a result, they have become indispensable tools for both tactical strikes and strategic deterrence. Propulsion systems. The heart of any cruise missile lies in its propulsion system, which must provide sustained thrust over long distances while maintaining fuel efficiency and compact design. Most modern cruise missiles employ turbofan or turbojet engines, similar to those found in commercial aircraft, but scaled down and optimized for single-use applications. The Tomahawk cruise missile, for example, uses a Williams F-107 turbofan engine that produces approximately 600 pounds of thrust, enabling the missile to maintain subsonic speeds of around 550 miles per hour throughout its flight. The engine intake system is carefully designed to capture and compress incoming air efficiently, while the missile travels at various altitudes and speeds. Internal fuel tanks store jet fuel that powers the engine throughout the mission, with fuel consumption calculations precisely programmed to ensure the missile reaches its target. Some advanced cruise missiles incorporate ramjet or scramjet engines for hypersonic capabilities, though these require more complex fuel systems and present significant engineering challenges related to heat management and materials science. Navigation and guidance systems. Modern cruise missiles employ multiple redundant navigation systems to ensure accurate target acquisition, even in contested electronic warfare environments. The primary navigation system typically relies on global positioning system satellites, which provide continuous position updates with accuracy measured in meters. However, since GPS signals can be jammed or spoofed by adversaries, cruise missiles incorporate additional navigation methods as backup systems. Inertial navigation systems use gyroscopes and accelerometers to track the missile's position, velocity, and orientation relative to its starting point. These systems operate independently of external signals, making them immune to electronic jamming, though they can accumulate small errors over long distances. Terrain contour matching systems compare the missile's current altitude readings with preloaded digital terrain maps, allowing the weapon to correct its course by matching geographical features below. Digital scene matching area correlation. Systems take this concept further by comparing real-time optical or infrared images of the terrain with reference images stored in the missile's memory. This technology enables incredibly precise terminal guidance, allowing missiles to distinguish between closely spaced targets or identify specific buildings within urban environments. Flight control and maneuvering. Sophisticated flight control systems enable cruise missiles to navigate complex, three-dimensional paths while avoiding obstacles and maintaining stealth. Onboard computers rapidly process sensor inputs and adjust control surfaces like rudders and elevators. Some systems use thrust vectoring for enhanced maneuverability, allowing the missile to fly precisely along its designated route. Cruise missiles often fly at very low altitudes, sometimes just 50 to 100 feet above ground, to evade radar. Advanced algorithms guide this terrain-following flight by analyzing terrain and weather data in real time. Many missiles follow preset waypoints, while others receive mid-flight updates, enabling retargeting, loitering, or mission aborts. Warhead and terminal guidance. The warhead section of a cruise missile is tailored for specific targets, from hardened bunkers to naval vessels or precise strikes requiring minimal collateral damage. Conventional warheads use high explosives with shaped charges or penetrating designs, while nuclear variants offer strategic deterrence with adjustable yields for mission flexibility. In the final approach, terminal guidance systems enhance accuracy by shifting from GPS to optical or radar targeting. ADAS, often supported by AI to identify real targets and avoid decoys or civilians. Fusing systems determine optimal detonation. Impact, delayed, or proximity, using advanced sensors and backups to ensure precise, reliable warhead function. Stealth and countermeasures. Stealth technology is essential for cruise missile success, enabling them to bypass advanced air defense systems. Key physical features include angular surfaces to deflect radar, radar-absorbent materials to reduce detection, and carefully engineered engine designs to limit infrared visibility. These elements work together to minimize the missile's radar and heat signatures throughout its flight. Electronic countermeasures enhance survivability with radar jamming, chaff and flares to mislead interceptors, and frequency-hopping communications to resist jamming. Some missiles adjust their flight patterns in real time to evade threats. Their small size, low-altitude paths, and unpredictable approaches make them difficult to detect, complicating defense strategies and increasing strike effectiveness. Modern developments and future technologies. Modern cruise missile development emphasizes greater range, precision, and affordability through modular designs. Artificial intelligence enables autonomous target recognition and decision-making, reducing reliance on preset plans. Swarm capabilities let multiple missiles coordinate attacks, overwhelming defenses with synchronized or staggered strikes. Increasing effectiveness against even the most advanced interception systems. Hypersonic cruise missiles, traveling over Mach 5 with high maneuverability, pose serious challenges to current defense technologies, but require complex, costly materials and propulsion systems. Network-centric integration allows real-time updates and coordination with other assets, enhancing adaptability. Future innovations may include recoverable surveillance variants, EMP warheads, and advanced AI capable of fully autonomous mission execution. Conclusion. Cruise missiles exemplify the convergence of multiple advanced technologies into highly effective weapons systems that have fundamentally altered modern military strategy and tactics. Their combination of precision guidance, stealth capabilities, and flexible engagement options provides military commanders with unprecedented strike capabilities across vast distances, making them vital tools in both offensive and defensive operations. The continuous evolution of propulsion systems, navigation technologies, and artificial intelligence ensures that cruise missiles will remain relevant and increasingly sophisticated. As defensive technologies improve, development now focuses on countermeasures, swarm tactics, and hypersonic capabilities. Understanding these complex systems offers insight into current military strengths and the technological challenges that fuel ongoing global defense research and innovation.